All right, so this is the energy of a photon. Right, so this is Planck's constant. What is that? It's in the front of the packet, 6.626 times 10 to the minus 34 joule seconds, right? And then this is the frequency. Right? Remember that the frequency is just c over lambda, right? So you can also say that the energy is hc over lambda, right? That's kind of fun, right? Okay. This is a formula for the wavelength, which is just, we've just rearranged this, right? They put the lambda up there, right? So it's hc over E. Now, check this out. This is kind of fun. Do you see how they're giving you different values of hc, right? Okay. If they give you joules, of energy, then use that, right? I.e., let's imagine we've got a photon energy of 1.2 times 10 to the minus 18th joules, right? The wavelength would be lambda is equal to, and then we'd use this guy, right? So 1.99 times 10 to the minus 25th joule meters, right? Divided by 1.2 times 10 to the minus 18th joules. So 1.99 E minus 25 divided by 1.2 E minus 18 would give us 1.658 times 10 to the minus 7th meters, right, of wavelength, okay, which would be like 165 nanometers. It wouldn't be visible, right? Okay, let's imagine that if I gave you that the energy was 5.2 electron volts, then you could find the wavelength, right? You could use this guy. Right, so wavelength is 1 point, because notice that joules and joules cancel, right? We could use 1.24 times 10 to the minus 6th electron volt meters, divide by 5.2 electron volts. And notice that it's gonna cancel, we'll get meters again, right? So 1.24 E minus 6 divided by 5.2. This just makes it easier. So I get 2 point, this is also not visible, 38, this is like ultraviolet or something like that, times 10 to the minus 7. So that'd be 238 nanometers. Again, we couldn't see that, but there it is, right? All right. So that's what these things are for. This is just a very handy way to relate the energy of a photon to its wavelength.